In this video, we're going to learn how to graph sine functions. In particular, we're going to look at how to graph y equals 2 times sine of 2x plus pi thirds all minus 1. And this follows from the general type of sine functions written here, y equals a times sine of bx plus c plus d. So to start with, we're going to find the period. Remember that the fundamental period of sine is 2 pi. So we're going to divide this by b, which is the coefficient of x inside the argument of sine, to get the period of our particular sine function. In our problem, b is equal to 2, so to get the period, we're going to do 2 pi divided by 2, which is pi. And therefore, this is now our period. So if I look at here step 2 for a moment, if I look at the length of one cycle from the beginning to end, this would be pi. And that's our period. Okay, the next step is to find the 5 points. Okay, these are the 5 important points that make up one cycle. Now what we're going to do is we're going to start by finding the x coordinates of these points. Okay, so let's do that. This is actually the x coordinate. The first point comes from setting the argument, which is 2x plus pi over 3 equal to 0, and solving for x, which you get negative pi over 6. Okay, now that serves as the first point. It's also called the phase shift. We'll see why in a minute. Now, going back to this diagram here on the left, we see that if I divide the period into 4 parts, that'll give me the other 4 points. So this distance here is the period, which is pi divided by 4. Similarly, this distance here is the period pi divided by 4. Continuing in this way, we're going to learn how to find the other 4 points. Okay, so for example, to find the second point here, we're going to take the first point, which is negative pi over 6, and we're going to add pi fourths. Of course, the common denominator here is 12, so this would be negative 2 pi plus 3 pi all over 12, which gives us pi over 12. Okay? Of course, pi over 4 can also be written as 3 pi over 12. So by just adding 3 pi over 12 to each successive point, we get the next point. So for the third point, we'll get 4 pi over 12. For the fourth point, we'll get 7 pi over 12. And for the fifth point, we will get 10 pi over 12. Okay? So those are the 4 points, or the 5 points, that are going to make up one cycle. Okay? Now, next comes the vertical shift. Now, the vertical shift is determined by this quantity that's added or subtracted to the rest of the function. In our case, that number is d. So here, for step 3, we have d equals negative 1. And that means we have a vertical shift of 1 unit down. So, one thing that helps us determine is this very special line that goes right across this one here, and that's the equilibrium line. And so we can label that as y equals negative 1. Okay? So far, let's plot what we have. Okay? So we'll start with the x-axis. Let's put it here. Okay? And we'll make each unit equal to pi over 12. So the first point is negative pi over 6, which can also be written as negative pi over 12. Okay, so we'll put that here as our first point. It's negative pi over 12, or maybe you can even write it up here. Okay, and so this point is 0 pi over 12, and this point is pi over 12, and then this point is 4 pi over 12, and this point is 7 pi over 12, and finally this point is 10 pi over 12. Okay, and that 0 is where the y-axis is going to go. So this is your x-axis, and this is your y-axis. And the last thing we did is we had this line of equilibrium, which was at negative 1. We'll choose 2 squares to be 1 unit on the y-axis. So here, I'm going to graph the line of equilibrium, okay, and I'll label it y equals negative 1. Okay, so the next thing we want to know is what is the shape of our function, okay? And the shape depends on a. A is the multiplier of the sine. In our case, a is 2. And the sine of a will tell us whether it's going to be this shape here if a is positive, or this shape down here if a is negative. So a in our problem is 2, which is positive, so we're going to have this shape. In other words, after the first point, we immediately go up to the maximum. Okay? And the next thing we have to figure out is the amplitude. And the amplitude is the absolute value of a, which is the absolute value of 2, and that's 2. And the amplitude tells us how far up or down we're going to go to find the highest and lowest points. In our problem, that's 2. Okay? So this is what we have so far, and let's copy this to our next slide and put all the information we've learned together. So here we are. The 5 points start at, since we have this positive shape, start at the equilibrium. So that's the first point. And then they go to the highest point, which is 2 units above, which is right here. That's 2 units above the equilibrium. Okay. And then we go back to the equilibrium. And then for the fourth point, we go down to the lowest point, which is, again, 2 units below. It's right here. Okay. So that's this point here. And then for the last point, we go back to the equilibrium, just right here. Okay, so now these 5 points will determine the shape of our sine function. So if I join these points now, using the shape that we've determined, we have a graph of 1 cycle of the sine function. Okay, so let's look at these 4 properties that we see here. First, let's mark the period on the graph. This distance here is the period, which is pi. The next is the phase shift, which is how far left or right you go from the y-axis. In this case, we went left, so that's our phase shift, and that was negative pi over 6. We made a little mistake here. This should be 2 pi over 12, so that's pi over 6. And then we had a vertical shift. Let's get rid of this. Let's get rid of this. So we had a vertical shift of 1 unit down. So that's going from the x-axis down 1 unit. That's our equilibrium. And then finally, to get the vertical maximum and the minimum, that was the amplitude. Okay, so here we've determined the amplitude, which is 2. Amplitude is 2, and this was the period, and in purple we put the phase shift. So there you have it. In 5 easy steps, we've learned how to graph the sine function. And this works for any general sine function that's written in the standard form of a times sine of bx plus c plus d.